Hello everyone, I'm happy to introduce our paper, A Backpack Full of Skills, Egocentric Video Understanding with Diverse Task Perspectives. What can we learn from a single video? Different egocentric video tasks can provide different and possibly complementary perspectives on what the user is doing. There are different approaches that can be used to learn from these tasks. For example, single task models learn unique weights for each task. Multitask learning shares a common backbone among the different tasks, with small task-specific heads on top. Task translation is a more recent approach that learns to translate the contributions of different tasks to solve one of them. These approaches have some limitations. For example, multitask learning can share weights across different tasks, but it does not explicitly model cross-task synergies and can lead to negative transfer between tasks. Likewise, the cross-task translation mechanism proposed by EgoT2 combines different perspectives from different tasks, but it needs to know all the tasks beforehand, and it requires separate models for each task. We propose an approach to overcome these limitations that focuses on knowledge reuse across different tasks. To do so, we adopt a temporal graph-based shared model, and the goal is to outperform both single and multitask baselines adapted to our knowledge reuse scenario. Our approach is called EgoPack and is composed of two stages. In the first stage, a multitask model is trained on a set of k known tasks. In the second stage, the same model is fine-tuned on a novel task using the cross-task interaction mechanism of EgoPack. To share the same model across different tasks, we propose to model videos as graphs. The nodes of these graphs represent temporal segments of the video. Edges connect temporally close nodes, depending on the task at hand, and egocentric video tasks can be represented as different graph operations, such as node classification and graph classification. By doing so, we can model temporal reasoning using a graph neural network that iteratively updates the node representations using message passing. This allows to unify all the considered tasks under a shared temporal model. Finally, a set of task-specific heads projects the nodes in the output space of each task. In the second step, we want to learn a novel task using the cross-attention mechanism of EgoPack. When fed with the same video, all these task-specific heads model different and complementary perspectives on the content of the video. We can collect these perspectives in a set of action-wise task-specific prototypes. We call these prototypes a backpack of skills that can be reused when learning a novel task. They represent a frozen snapshot of what the model has learned in the pre-training phase on the k known tasks. To learn a new task, for example, object state change classification, we add an additional task-specific head and combine its output with the contributions coming from the different pre-training tasks. More practically, we feed the node representations coming out of the temporal graph neural network through all the heads of the k known tasks. Then, we use these task-specific representations to find their closest matching prototypes using a k-NAND search in the feature space, and refine their representations using message passing with the closest prototypes. Finally, we compute a prediction using the perspective of each task, so using the features of each task, and sum their contributions with the output of the new head for the novel task. We validate our approach on 4 human-object interaction benchmarks from Ego4D: action recognition, object state change classification, long-term anticipation, and point of no return. We compare EgoPack against the Ego4D single-task baselines and EgoT2, both trained end-to-end. We also include a comparison between a simple MLP baseline and our GNN-based temporal model to validate our choice to use a graph-based representation as the main building block of EgoPack. We also compare with both multitask learning approaches and task translation approach adapted to our scenario, showing a clear advantage of EgoPack thanks to its ability to reuse the learned knowledge. We also evaluate EgoPack on the test set of the Ego4D challenges, showing that EgoPack clearly outperforms competitors under comparable conditions. In terms of visualizations, the cross-task agreement plots show how much different tasks agree or disagree with each other, which determines their ability to bring complementary insights when learning a novel task. We also show which prototypes are matched in the k-NAND feature space, showing that some prototypes appear to be more discriminative than others when learning a novel task. Thank you for your attention.